Okay, so moving right along, we're talking now about our ionization energy. And again, all that really is, folks, is another trend that we can see on the periodic table. We've noticed the trend, well, of course, of electron configurations and orbital diagrams, but we've also now seen the size of atoms and ions, of course, by that matter. Ionization energy, big word, pretty simple. The amount of energy required to lose an electron. So, each time an atom loses an electron, it costs it some energy. Okay, it costs it some energy. And so that amount of energy required to lose an electron is what's called ionization energy. Now it deals with size. Okay, so let's take a look. Let's say we have, well, let's draw here in yellow. I think that'll. Protons, electron on the outside versus proton, electron on the outside. Okay? Which one of those do you think the proton-electron attractiveness is greater? I hope you're thinking that, notice the distance between the protons and the electrons versus the distance here. The smaller the size, the larger the ionization energy. And the reason that is this. If the ionization energy is the amount of energy required to lose an electron, this electron on the right, on the left here near this small one, is being held a little bit tighter because it's closer versus this electron over here. Okay, it's holding on a little loosely, as 38 Special might say. Okay, take two magnets, hold them together. When they're pretty close, you can actually feel them wanting to pull together, right? If they're the opposite ends, of course, and they're attracting. You can feel them wanting to pull together. If you hold those exact same magnets far apart, they're the same ones. They have the same attractive forces. But because they're further apart, you're not feeling that tightness kind of pulling them together. So that's what happens in this one, where a large atom, because the electron is so far away, it kind of would allow it to lose a little bit easier. So ionization energy in terms of, whoops, ionization energy is the amount of energy required to lose an electron, and it's the exact opposite of size, because the smallest ones, all right, the smallest ones are going to have the larger ionization energy. So here's my periodic table again. I'll just draw it very general. Okay, if size goes down and to the left, larger, then ionization energy is going to be the exact opposite, up and to the right, large ionization energies. Okay, because they're smaller, so they're being held a little more tightly together. Okay, the only little wrinkle I would also, so again, all I'm going to do is compare, you know, compare oxygen and potassium. Well, oxygen's over here, potassium's over here. Oxygen's going to have a higher ionization energy. Okay, the only little wrinkle is that when we compare noble gases, okay, so if we compare noble gases, oops, let me write it where you can probably see. Okay. We're going to say that noble gases have higher ionization energies than other things. Why? Because if the ionization energy is the amount of energy required to lose an electron, noble gases don't want to lose them at all. Okay? They don't want to lose them at all. They're already very stable. So even if you compared, let's say, xenon down here with fluorine, if I asked which one was larger, definitely xenon is larger, okay, because it's down quite a bit compared to fluorine. But even though it's larger than the fluorine size, its ionization energy is going to be bigger because it's a noble gas and it doesn't want to lose electrons at all. Okay? The only other thing I want to mention about ionization energies is that you can tell what family something is in by looking at ionization energies. There's actual values, okay? Something called successive ionization energies. Now, let's say we're talking about, oh, it could be anything, sodium, right? Sodium has 11 electrons when it's an atom, right? Because it's sodium, it has 11 electrons. How many electrons could it lose? It could lose all 11. It could lose all 11. And so since it could lose all 11, there's going to be values, energies, ionization energies associated with each electron. When I say first, second, third, fourth, what I'm talking about is the successive ionization energy, you know, losing the first electron, the second electron, etc., etc. Okay? What this will tell us is wherever there's a huge jump in ionization energies, that's where the atom, which has now become an ion, is very happy. It doesn't want to lose the next one. So take a look at these. Our first ionization energy, okay, 680 kilojoules. Our second costs it 915, let's say. I made these numbers up. The third, notice there's a large jump. We're going from 900 to 6,000. And then, of course, this next one is not quite as big a jump either. So what we have is we have a large jump between the second and third ionization's energies. Okay? So since there's a large jump there between the second and third, then what it means is whatever this atom is, and I'm going to put since large jump between the second and third energy ionization energies, then it must lose 2 electrons. I'll put easily, I mean relatively easily, then not want to lose the third, right? Because it's so high. So what family, what group, what up and down, would lose 2 electrons pretty easily, but then not want to lose a third? Well, the ones that, once they've lost 2, they're a noble gas. So if we look at our periodic table again, okay, we could assume that this element must be in the alkali metals because it loses 1 and then loses, remember we're going now over to the noble gases, it's now like a noble gas, so it loses 2 electrons, and it doesn't want to leave the noble gas. So since there's a large jump between the second and third, it must be an alkaline earth metal. Okay? Because it's lost 2. If there would be a large jump between the first and second, it would have been in the alkali metals. If it's third and fourth, we're skipping our middle. Skip your, just like we did when we were going 1 plus 2 plus, skip the middle, 3 plus. Skip the middle, where we would then, you know, talk about, I should put aluminum at the top, we should put boron at the top, you know, the boron family. Okay, 1, 2, 3. If there's a big jump between the third, it would be boron. Okay, so skip your whole middle, and then you're basically looking at the S&P block. And that's how you read successive ionization energies to figure out what family something might be in.